Hello, and welcome back to the course on Physics for Engineers. So, in this lesson, we will still be continuing the topic on geometric optics. But before we proceed with this lesson, let us first discuss some review. So, in the previous lesson, when we introduced the topic of geometric optics, we have discussed that an image can be described based on its nature and orientation. Its nature can be real or virtual. It can be a real or a virtual image, and its orientation can be an erect or inverted image. We also have discussed about the different object and image quantities such as the distance, height, magnification, and the focal length. And lastly, we discussed about the sign rules in geometric optics. So when does the distance become positive or negative? The height becomes positive or negative? When does the magnification becomes positive or negative? And when does the focal length uh, uh, becomes positive or negative? So in this lesson, this is Geometric Optics Part 2. We will be focusing on how images are formed in mirrors. So let's start with plane mirrors. So in plane mirrors, the images that you see are actually reversed, and they are both virtual and erect. So you see a virtual image of yourself when you look at a mirror, and the image is erect, meaning it will have the same orientation as you, even though the images are reversed. The right becomes left, and the left becomes right. So in plane mirrors, the relationship between the object and the image distance is that the image distance s prime is equal to the negative s. So the negative sign just implies that the image is virtual. But essentially, the height of the image and the height of the object are the same. When you look at a plane mirror, whatever your height is, that is also the height of your image. So same height, and meaning if they have the same height, then the magnification is just y prime over y, the ratio between the image height and the object height, and you will get +1. So these are the object image relationship for plane mirrors. Same height, and then magnification is positive, meaning it's erect, and it's 1, meaning it's neither larger or neither smaller than the object, it's the same height. So let's now go to spherical mirrors. Now there are two types of spherical mirrors, the concave mirror and the convex mirror. So a concave mirror is a mirror where the surface seems to have a depression in the form of a sphere. Sometimes it's also called a converging mirror. We will see later why it's called a converging mirror. A convex mirror, on the other hand, seems to have a bulge still in the shape of a sphere, and sometimes it's also called referred to as diverging mirror. So this is a concave mirror. So there's a depression, and in the convex mirror there's a bulge. It's bulging out. Here it's a depression. So we have discussed about the center of the mirror, the focal point of the mirror, the radius of curvature of the mirror, and the focal length of the mirror. Now, in the case of a concave mirror, its radius of curvature is positive, meaning its focal length is also positive, since the focal length for spherical mirrors is just 1/2 the radius. For convex mirror, the radius of curvature is negative, meaning the focal length of convex mirrors are also negative. So one example of this is a spoon. So if you look at a spoon in this manner, you see the depression, that's actually the concave part. But if you reverse the mirror on the back side, when it's now bulging, that's actually a convex mirror. And you will see, you will notice that there are different images formed here. You will see that the image that you see here is inverted, here it's erect. So the object-image relationship in spherical mirrors is given by this equation. So 1 over S, S again is the object distance, S prime is the image distance, and then F is the focal length of your spherical mirror. So focal length is positive for concave or converging mirrors, negative for convex or diverging mirrors. So this image or diagram that you see here is what we call array diagram. So array diagram is the graphical method of image formation. So this is the mathematical method of finding the image, S prime. And what you see here is the graphical method of image formation, where you use rays to find the image. Now, in ray diagram formation, for concave mirrors, we will be discussing 4 principal rays. So primary or principal rays. So an incoming ray parallel to the axis will be reflected passing through the focal point. A ray passing through the focal point will be reflected parallel to the axis. A ray passing through the center will be reflected passing through the center. And a ray passing through the vertex will be reflected at an angle according to the law of reflection. Okay, so suppose we have an object with height y, with distance s from the vertex, and this is our concave mirror. No. So the first principal ray is the ray parallel to the optical axis, and this will be reflected passing through the focal point. So that's the first, the principal ray, or ray number 1. Now, a ray passing through the focus will be reflected parallel to the axis. So that's ray number 2, the second principal ray. And then ray number 3, ray passing to the center, will just be reflected back, passing to the center, ray number 3. And ray number 4 is the ray passing to the vertex, will be reflected according to the law of reflection. So the angle of incidence here is just the angle of reflection here. That's ray number 4. So those are the 4 principal rays. And you will notice that all of these rays converge at this point here. Meaning, this point corresponds to the point in the object here. So meaning the head of this object is now located here in the image. So the image is now here. The image of this arrow, our object, will now be here. So we'll notice all of the rays are converging at that point. So what you will see will be a real inverted image. And hence, a concave mirror is also called a converging mirror because most of the time, the reflected rays are converging to form the image. So S prime here is positive because it's a real image. And since it's inverted, the magnification is negative. Okay. Suppose we have another situation where the object is at the center. So if the object is at the center, this is the first ray, ray number 1. Ray parallel will be reflected passing through the focal point. Ang ray passing through the focal point will be reflected parallel to the axis, ray number 2. Ray number 3, there will be no ray number 3 because it's at the center. Then ray number 4, passing through the vertex, will be reflected according to the law of reflection. Okay, so in this case, you will notice that all of the rays converge at this point, meaning the image is at that point. So when your object is at the center of the concave mirror, its image will also be at the center of the concave mirror or converging mirror, but it will still be, and the image will still be real and inverted image. But you will see here that they will have the same height, but the magnification is negative here because it's inverted. So if the object now is between the center and the focus, so this is the ray diagram formation, ray number 1, ray number 2, ray number 3. Oh no, there's no ray number 3, ray number 4 only. And the image will be located at the back of the center. So, yeah, behind the center. It will still be a real and inverted image. If For instance, the object is at the focal point. So what you will see is that's the primary ray, and that's the fourth ray, ray number one, ray passing through the vertex. And you will notice that these two rays are actually parallel to each other. And what you will see is an image at infinity, or basically when the image is at infinity, infinity doesn't exist. There's no image form. So the image is formed at infinity, meaning there's no discernible image that is formed or that you can see when the object is placed at the focal point. Again, we are still on concave or converging mirrors. So lastly, if the object is placed between the focal point and the vertex, this region here, what you will see is this one. So what you will see is actually a virtual and erect image. So this is the condition where the rays in a concave mirror or converging mirror are actually diverging to produce a virtual and erect images. So images near, very near, inside the focal length of a converging or concave mirror will actually produce virtual and erect images. And this is the technology behind magnifying mirrors. So I'm sure most of you girls have a magnifying mirror for your makeup stuff. So what you're using actually there is a concave or converging mirror, and the object, your face, is actually between the focal point and the vertex of that mirror. And what you will see is a magnified, a larger image, larger than the object, and it's erect. The same orientation, but it's a virtual image. So virtual and erect image, which is actually magnified, a larger image. So that's one application of concave mirrors. So let's now go to convex mirrors or diverging mirrors. So these are the four rays. I'm just gonna go through with the animation here. So in a convex mirror, there's no special situation, no, because the object is always the vertex, the focal length, and the center of curvature is inside the mirror. So it doesn't matter where your object is because it's in this side always. So a ray parallel to the mirror will be reflected as if it's coming from the focal point. A ray that is going through the focal point will be reflected as if it's parallel to the axis. That's principal ray diagram, principal ray number 2. A ray passing to the not passing but going or pointing towards the center will be reflected back, and a ray passing through the vertex will be reflected according to the law of reflection. So you will notice the four principal rays: ray number 1, ray number 2, ray number 3, and ray number 4. They're spreading, they're diverging. That's the reason why convex mirrors are also called diverging mirrors, because the reflected rays are diverging. But these diverging rays are seem to actually come from this point here. So meaning this is the image point of the point on this object here. So the image is actually formed, in this case, in this region here. So what you will see is a virtual erect image, but it is a smaller image. It will always be a smaller image. It will be demagnified. So if you have an object in front of a convex mirror, it will always be smaller. It's virtual, it's erect, the same orientation as the object, but it will be smaller. So that's for diverging mirrors. So a convex mirror actually gives you a wide field of view. That's why most convex mirrors are used as security mirrors. So in the old in the old days, or if you have an old grocery store, you will see security mirrors like this. But right now, they're now using CCTV cameras. So objects seen in a convex mirror are actually closer than they appear, and that is actually written in your side mirrors of your car or your motorcycles. So there's always note there that the objects that you see in a convex or diverging mirror are actually closer than they appear, because what you see here are the you will the images are actually smaller That's why if the object is small, you will associate that as being far. But it's actually not. It just becomes smaller, but it's actually not far, but very close. So be careful when looking at convex mirrors. So let's have an example. So a concave mirror, so this is our mirror, forms an image on a wall 3 centimeters from the mirror of the filament of a headlight lamp. So basically you can think of it as a headlight lamp of your car, or a flashlight rather. It's just the same principle. You'll notice that a headlight or a flashlight has a reflecting surface at the back, and then you put the uh, bulb here. So the bulb has a filament, and that filament is our object. So our object here is self-luminous. It has its own light. It generates its own light. So the filament of a headlight lamp, 10 centimeter in the front of the mirror. So this distance is 10 centimeter. It forms an image on the wall. The wall is here. Image of this filament here. And the wall is actually 3 meters from the mirror. So basically you have a headlight lamp. You shine it on the wall and you see some lines, some images of the filament of the light bulb. So the question now is, what are the radius of curvature and focal length of the mirror? And what is the height of the image if the height of the object is 5 millimeters? If the object height is 5 millimeters, what is the height of this image here, y prime? So this is a converging mirror, so the radius of curvature and the focal length are both positive, and the focal length is just 1/2 of the radius. Okay, so for letter A, uh, we need to find the focal length or and the radius of curvature. And we use the object image relationship for spherical mirrors. So 1 over s plus 1 over s prime is equal to 1 over f, or since the focal length is radius over 2, then this is also equal to 2 over r. So solve for r in this case, and you get this one. Manipulate the equation to get this one. And substitute the values. S is 0.10 meters. S prime is 3 meters. 0.10 meters, we converted the centimeter to meter here, and then plus 3 meters. And you will get the radius of curvature to be 19.4 centimeters. 0.194 meters or 19.4 centimeters. And half of this is the focal length, 9.7 centimeters. Now for letter B, what is the height of the image? So height, you can solve for the height by using the magnification formula. So you have y prime over y is equal to negative s prime over s. So solve for y prime, and then we get y prime cross multiply y there. We have negative s prime over s times y. So we are given with the s prime 3 meters. We're given with the object distance 10 centimeter or 0.10 meters. We're given the height 5 millimeters. We need to convert that into meters, 0.005 meters. And we get a value of negative 0.15 meters, or that is negative 15 centimeters. So the height is negative. So when you take the magnification, the ratio of the height of the image and the object, we'll get a negative result. So the magnification will actually be, in this case, the magnification is actually negative 30. So the magnification is negative 30. So the negative sign will imply that the image will be inverted. So as you can see here, the arrow is inverted. And the size is actually 30 times magnification. So if you take the ratio of negative 15 centimeter and the height of the image is 5 millimeter, that's actually 30. So negative 30. The magnification is negative 30. So the negative sign means it's inverted. And the 30 means it's magnified 30 times. So 5 millimeter, it's magnified 30 times, it becomes 15 centimeters. So this is actually how a light bulb is placed inside a flashlight or a headlight lamp. So bulbs are placed closer to the focal point of the mirror so that light rays will emerge as nearly parallel beams. So if you'll notice, the focal length of this mirror is 9.7 centimeters, and you place your object at 10 centimeters, which is very close to 9.7 centimeters. So from the principal ray diagram, a ray passing through the focal point will emerge parallel to the axis. So in this case, since this is not exactly at the focal point, the object is not exactly in the focal point, it's nearly parallel. So that's a concept of how to focus the light in a flashlight or headlamp. So they use a converging or concave mirror. So example number 2. So image formation by a convex mirror now. So our convex mirror now here is a Christmas tree ornament. So a Christmas ball, a shiny Christmas ball which can now serve as a mirror. So Santa, supposedly, this is Christmas, a Christmas problem. Santa checks himself for suit uh, using his reflection in a shiny silvered Christmas tree ornament 75 centimeters or 0.750 meters away. So the diameter of the ornament is 7.20 centimeters. Standard reference work states that he's a right jolly old elf, so we estimate his height to be 1.6 meters. So where and how tall is the image of Santa formed by the ornament? Is it real or virtual? Is it erect or inverted? So we are now talking about where the image distance and how tall the image height. So obviously, the image that you see here will be virtual and erect because for diverging mirrors or convex mirrors, the image is always virtual and erect and the image is always smaller. So this is the principal ray diagram for this problem. So you have Santa represented by this arrow, 1.6 meters, and this is his image here. We don't know his height yet. We don't know the distance yet, the image distance. But this is virtual, so this S prime should be negative. And since this is erect, Y prime should be positive. Okay. So the radius, the diameter of the ornament is given by 7.20 centimeters. So meaning we can get the radius. Half of that is the radius. That's the diameter, sorry. Half of that is the radius. So the radius is 3.60 centimeter. Half of the diameter, 720. And then half of the radius is the focal length. So the focal length is half of the radius or 1/4 of the diameter. So in this case, the radius is negative because this is a convex or diverging mirror. So meaning the focal length is also negative. So take note of that. The focal length and radius of curvature are negative for diverging or convex mirrors. So we can now solve for S prime. So we know the focal length, it's negative 1.80 centimeters. We know S, it's 75 centimeters. So the unknown is S prime. To solve for S prime, so substitute the values and you will get S prime is equal to negative 1.76 centimeter. Again, the negative sign here implies that the image is virtual. A negative distance means that object or that image is a virtual image or object. So to solve for the height, we use the magnification formula. So solve for y prime, and you will get y prime is negative s prime over s. So substitute all of those values, and you will get y prime is positive 3.8 centimeters. So again, positive y prime means, oh no, if the y prime is positive and the y is also positive, they are both the same sign, then the image is erect. So in this case, the image is erect because the magnification is positive. It's actually the ratio of y prime and y, which is 1.6 meter, is actually plus 0.024. The positive sign implies that it is an erect image. So that one. But you will notice that the magnification here, the value is less than, very much less than 1. So it's demagnified. So the image of Santa fits in the inside the Christmas balls. So that's the end of this lesson on Geometrics 2 image formation in mirrors. Now, in the next lesson, we will still continue with the topic on geometric optics, and we will be discussing about image formation in thin lenses. So I will see you again next time.